The RLC series circuit. An RLC series circuit consists of a capacitor with capacitance 2.5 microfarads, an inductor with inductance 5 millihenries, and a resistor with resistance 75 ohms connected across an AC source of voltage amplitude V equals 15 volts having variable frequency. Part A. Under what circumstances is the average power delivered to the circuit equal to 1 over 2 V RMS I RMS? So we can see that in this circuit, the charge that will be stored on the capacitor Q is equal to the voltage across the capacitor plates multiplied by the capacitance. So the current that flows through the capacitor is I is equal to C dVc dt, and therefore the voltage across the capacitor Vc is equal to 1 over C integral I dt during the charging process. I also have the resistive reactance R, the capacitive reactance 1 over omega C, the inductive reactance omega L, and we're looking for an average power P average, which is also shown with angular brackets, to be 1 over 2 V RMS I RMS. Now normally this is V RMS I RMS times the power factor cosine phi. So we want this to be 1 over 2 V RMS I RMS. So this implies that cosine phi, the power factor, should be equal to 1/2. So here cosine phi is the power factor. So cosine phi is equal to 1 over 2 implies phi, the phase angle, to be 60 degrees. So it's cosine 60, which is sine 30. Now, if I write the Kirchhoff voltage law equation for this loop here, so if I follow this loop here and write the Kirchhoff voltage law, the voltage across the resistor, which is I times R, plus the voltage across the inductor L di dt, plus the voltage across the capacitor 1 over C integral I dt is equal to the source voltage V. Now, the current that flows in the circuit, I of t, let's say is I sine omega t. Then you have the voltage across the resistor equal to I times R sine omega t. The voltage across the inductor VL is equal to I omega L cosine omega t, because it's the derivative, which is I omega L sine omega t plus pi over 2, sine omega t cosine pi over 2, which is 0, times plus cosine omega t sine pi over 2, which is cosine omega t. And the voltage across the inductor, Vc, is I divided by omega c sine omega t minus pi over 2. So we have this phase relationship between the voltages. So you can see that we can represent this in a phasor diagram. The inductive reactance XL, resistive reactance XR, and capacitive reactance XC. And we have a pi over 2 angle between each of these. So you can see here that for the inductor we have plus pi over 2, for the capacitor we have minus pi over 2. And this means that we can put all of this together. This will be equal to XL minus XC. And here we have XR and the impedance Z making an angle phi with respect to the x-axis. So we see that Z impedance times cosine phi is equal to R. So Z is equal to R divided by cosine phi. So cosine phi is equal to 1 over 2. That means Z is equal to 2R. At the same time, I have Z sine phi. Z sine phi is equal to XL minus XC, which is omega L minus 1 over omega C. So this is equal to 2R times sine 60, which is 2R square root 3 over 2. And the 2's will cancel, and I will be left with R square root 3. Okay. Now I can substitute the numbers for the inductance and capacitance for the given circuit. So let's do that. For XL, I have 5 millihenry, 5 times 10 to minus 3 omega. For XC, I have 1 over omega C, which is 1 over, it was 2.5 microfarads, 2.5 10 to minus 6 omega, which is 4 times 10 to 5 divided by omega. And XL minus XC, which is 5 times 10 to minus 3 omega minus 4 times 10 to 5 divided by omega, is equal to R square root 3, which is 75 square root 3. So I can solve for omega from this equation. So 5 times 10 to minus 3 omega square minus 4 times 10 to 5 is equal to 75 square root 3 omega, which can be written as omega square minus 25,981 omega minus 8 times 10 to 7. This is equal to 0. So we can solve for omega from this equation. Omega is 25,981 plus or minus, but because we cannot have a negative frequency, we will take the plus as the physical solution. 25,981 square plus 4 times 8, 32, 10 to 7, square root, divided by 2. So this gives us our final answer for omega. Omega is equal to roughly 28,800 radians per second. So this is our final answer for the angular frequency of the source. Okay, so that's basically answers the first question. When the frequency of the source is 28,800 radians per second, we have the required result. The average power is Vrms Irms cosine phi, which means the power factor is 1/2. Part B. Under the conditions of Part A, what is the average power delivered to each circuit element and what is the maximum current through the capacitor? So we're looking for the average power delivered to each circuit element and maximum current. Let's see. The maximum current, Imax, is equal to the maximum voltage, Vmax, divided by the impedance, Z. So the impedance of the circuit is square root of XL minus XC square plus R square. And I can calculate what XL is and what XC is. So XL is equal to omega L, which is 28,800 times 5 10 to minus 3. So this gives me XL is equal to 144 ohms. And for XC, I have 1/omega C, which is 1/28,800 times 2.5 10 to minus 6, 2.5 microfarads. So this gives me an XC value of 13.9 ohms. So from this, I can calculate the impedance. The equivalent impedance of the circuit, Z, is XL minus XC, 144 minus 13.9 square plus 75 square root. So this gives me, for the impedance of the circuit, 150 ohms. Therefore, the maximum current is the maximum voltage, 15 volts, divided by 150 ohms. The maximum current is 0.100 amperes. Okay. Now, what is the average power delivered to each circuit element? The average power delivered is Vrms, which is V divided by square root 2, Irms, maximum current, Vmax, Imax divided by square root 2, cosine phi, which is 1/2. So I have 15 times 0.1 divided by square root 2 times square root 2 is 2. Then I have another 2 from the power factor, so this is 4. So this gives me an average power equal to 0.375 watts. This is delivered to the resistor R. That's the average power delivered to the resistor. Now, what about the average power delivered to the inductor and the capacitor? Well, we can see that since the energy stored in the inductor and the capacitor, they oscillate in time, the average power that is delivered to the inductor and capacitor is 0. So for the inductor and capacitor, it's 0 watts, and for the resistor, it's 0.375 watts. So let's summarize what we did here. We have a series RLC circuit. So we want to know under which condition the average power delivered to the circuit is 1/2 Vrms Irms. The average power delivered to the circuit is Vrms Irms cosine phi, where cosine phi is the power factor, and this implies that cosine phi is 1/2 and this angle phi is 60 degrees, the phase angle. Now, for the voltage across the resistor, we have, let's show it here, this voltage VR, this voltage VL, and this voltage VC, and these voltages will add up to give me the source voltage. So I can see that I will have a loop here. The Kirchhoff, in order to apply the Kirchhoff voltage law, so this loop will indicate that the voltages across the circuit elements will add up to give me the source voltage. So this is my Kirchhoff voltage law, KVL loop. So the voltage across the resistor is IR in phase with the current. If the current is I sine omega t, the voltage across the resistor is IR sine omega t. The voltage across the inductor is L di dt, which is I omega L sine omega t plus pi/2. The voltage across the capacitor is 1/c integral I dt, which is I over omega c sine omega t minus pi/2. So because of this minus pi/2 and plus pi/2 here, when I plot the phasor diagram for the impedance calculation, XL minus XC is pointing up, making 90-degree angle with XR, and the impedance Z makes this angle phi with respect to the x-axis. So that's the phase angle we're talking about in the average power calculation. So that angle has a value of 60 degrees. So cosine 60 is 1/2, which means Z is equal to 2R, and sine 60 is square root 3/2. So that means we have 2R square root 3/2 is equal to XL minus XC. That's the information we have used to solve for omega for this quadratic equation, and we have found 28,800 radians per second. What is the maximum current that flows through the capacitor? It's the same current that flows through the resistor, inductor, and capacitor in series combination, so which is equal to Vmax divided by the impedance of the circuit. So plugging in the numbers for the inductance and capacitance, and I already know the resistance, I can calculate the impedance to be 150 ohms. So the maximum voltage supplied by the AC source divided by the impedance gives me the maximum current, 0.1 amps, and the average power delivered to the circuit, Vrms Irms 1/2, gives me 0.375 watts delivered to the resistor. But the average power delivered to the other two circuit elements, inductor and capacitor, is zero because the energy stored in these circuit elements oscillate in time, but the energy is being consumed by the resistor, and it's basically converted to Joule heating in the resistance of the circuit.